we are going to start with series LCR circuit. So in previous cases we have seen a single resistance, a single inductor and a single capacitor circuits, and we have seen and analyzed what will happen if we give a AC voltage to that source voltage to that particular circuit. Now we are considering a circuit where we have all the three components, that is inductor, capacitor and a resistor, and they are connected in series, and therefore the circuit is called series LCR circuit. L for the inductor, C for capacitor and R for the resistor. So now we are going to analyze how this circuit performs. So as we know, the source voltage here is a AC voltage. Therefore the voltage would be, let's suppose, V0 sine omega t. It means that the AC voltage is changing its direction, and it is changing its magnitude, and it is a sinusoidal change, and the frequency of this change is omega, denoted by omega. The peak value of the voltage is denoted by V0. So as we know this voltage is the source, then therefore let's suppose current I is flowing through this particular circuit, and this current I has a peak value I0. So let's suppose the current I is flowing with this current has a peak value I0. Then across this resistor there will be a voltage drop which we denote as VR. Across the inductor, the voltage drop can be denoted as either epsilon, but in this case we are taking it as VL. And across the capacitor, the voltage drop, let's suppose this is VC, right? So the peak value of all this, if we take, then the peak value of voltage V is V0. The peak value of VR would be I0 into R, as we have already seen, and the voltage VL would be I0 into XL, right, where XL is the inductive reactance. VC would be I0 into XC. So this capacitive reactance, inductive reactance, we have seen this when we were analyzing the circuit with individual components, right? But now we are dealing with a combination of all these three, and therefore the voltage drop across each element would be VR, VL and VC. Now this analysis we are going to do using a phasor diagram. So let's suppose this is a phasor diagram, and the current, let's suppose the current is I, is in this direction. So first we talk about the resistive element, that is the voltage drop across VR. So as we already know that in resistive circuits where we have a resistor and we give a AC source, the voltage and the current does not have any phase difference, so they would be in the same direction. So then we can say that the current and voltage, they are in same direction and their phase difference would be 0. Therefore, if current is in this direction in the phasor diagram, I can also show the VR, that is the voltage for the resistive element, in the same direction. So VR would be also in this direction, right? Now coming to the inductive part. As we know from our analysis previously, that in the case of the inductive element, when it is given a AC frequency, the voltage will lead. It means the voltage would be ahead of the current in the inductive case, and the phase difference between voltage and the current will be 90 degree or pi by 2. So if this is the current, then voltage would be at the 90 degree, that is in this direction. So this we can say as the direction of VL, because if this is the direction of the current, then for the inductive circuit it will be ahead, or it will be leading at 90 degree phase. So in the phasor diagram, VL will be pointed this side. Now coming to the capacitive voltage, and we know that in the case of capacitors, if the elements are capacitor element, then the voltage will lag behind the current by 90 degree. So if the voltage lags behind, it means it will still go down. Therefore VC will be in this direction, and again this is the 90 degree from the current, right? So we have shown all three voltages in this phasor diagram. If this is the current direction, then the resistive element will be the same direction as the current, because there is no phase difference. The voltage of the inductor element will lead than the current by 90 degrees, so this is in this direction, and the voltage of the capacitive element will be lagging behind by 90 degrees, so this is in this direction. Now let's suppose if we are choosing a particular for the calculation part, you see VC and VL, they are in opposite directions, right? So if I just try to bring it in this direction, then we can show this as minus VL, right? So this side we can show it as minus VL. Then probably this part we can write it as VC minus VL, right? So this part becomes VC minus VL. So I just say this is, if this is O, this is suppose A, this is B, this is C, and this particular place is D. Then with the vector VC minus VL and the vector VR, we are drawing a resultant vector V, right? Let's suppose this is E. So the projection here and the projection here, right? So little clearly if I draw, this is V. So this part we call it as VC minus VL, and this part is VR, right? So V is the resultant of VR and VC minus VL. Therefore we can write, suppose if this is E, this is O, this is A, and this is D points, then we can write OE square is equal to OA square plus OD square. So we will just substitute. This gives me V square is equal to VR square plus VC minus VL whole square, right? Now we will just put the maximum value for all this thing. We know the peak value will be V naught square. VR is I naught square R square, and this is I naught XC minus I naught XL whole square, right? So just pause this. So this is the calculation. So if we just go a bit further step, we can take out I naught square common, then this becomes R square plus XC minus XL whole square, right? And if we just take out the root, then it becomes V naught is equal to I naught into R square, sorry, root over of R square plus XC minus XL whole square, this whole root over, right? So you see here it's a very important term that is coming out, and as always we will first start to look at the current, right? We'll look at the peak current that is coming out from this circuit, and if we see this peak current I naught, this I naught is equal to V naught by this whole term, which is root over of R square plus XC minus XL whole square. So you see this is the resistive element of this particular circuit, right? So this is the resistive element that is coming out of this particular circuit, and this element we call it as impedance. We'll discuss about it in detail, but what we see, this is the impedance that is coming out of this particular circuit, and this is the peak current, and this is the voltage, and this is the impedance for a LCR series circuit. Now then, what about the current and the voltage phase? What would be the phase difference between them? So if I have to calculate the phase difference, suppose if this is the angle between, if this is phi, the angle or the phase, then we can write from this picture itself, or suppose if this is phi, then we can write tan of phi is AE divided by AO, or AE by OA, right? So this AE part is nothing but VC minus VL. So this is VC minus VL, and this part is VR. And if we just substitute that VC, VL and all, then we can write I naught into XC minus XL divided by I naught into R, and therefore this becomes XC minus XL divided by R. So this is the tan of phi, and then the phase phi would be tan inverse of this whole term, that is XC minus XL divided by R. So there is a phase difference between the voltage and the current. Why I have taken this angle? Because current is in this angle and the resultant voltage is here. Current is in this direction, resultant voltage is this direction. So there is a phase difference phi between the current and the voltage. And what would be the phase difference? That is given by this expression, that is phi equal to tan inverse XC minus XL divided by R. So if the case happens that if XC is greater than XL, then what we see, if XC, that is XC is greater than XL, then we see that this whole circuit tries to become like a capacitive circuit, means it is dominating on capacitor circuits. And then in this case we see the same thing happens which had happened during the capacitor circuit, that is the voltage lags the current. If XC is greater, then the voltage V will lag, and if XL is greater than XC, then the voltage will lead, right? If XL is greater than XC, if XL dominates over XC, then the circuit starts to behave like a inductive circuit. And if XC is greater than XL, then the circuit starts to behave like a capacitive circuit. And that's how what happens in a capacitor circuit, that is V lags behind the current, and how much it lags behind, that is given by the phase angle phi, which is given by phi equal to tan inverse XC minus XL by R. And if XL is greater than XC, then voltage leads, that is the current lags and the voltage leads. And how much will it lead? That also is by amount of phase angle phi, and that also is given by phi equal to tan inverse. But since it is XL is greater than XC, then in this term this will be XL minus XC divided by R. So that's what we have seen using this phasor diagram analysis, that in LCR circuit the combined effect of the resistive element is given by root over R square plus XC minus XL whole square. This is what is called the impedance of this circuit, which we'll talk in detail later. And also we see that there is a phase difference always, the phase difference between I and V, that is voltage and current, and this phase difference is given by tan inverse of XL minus XC minus XL divided by R. And if XC is greater than XL, then the circuits behaves like a capacitor circuit and the voltage would lag. And if XL is greater than XC, then the circuit would start to behave like a inductor circuit, inductive circuits, and voltage will lead. But there nonetheless there will be a phase difference which will be given by this particular equation.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.